Okay guys, sorry about the last video. My Surface hates me and hates children, so let's keep going. Okay, in this example, I want us to spend time at the beginning of class tomorrow to do an example of how G, K, and E are all related. So we'll do A and B together tomorrow. So let's just skip over this for right now. The last thing that we need to talk about in chapter 20 is the Nernst equation. Now, ultimately from chapter 19, and we pulled this earlier from chapter 19, except instead of thinking about it as Q, we thought about it as K before. So from thermodynamics, we know that delta G is equal to delta G standard delta G. So this is happening at 25 degrees Celsius. And I can add that to RT, L, and Q. Q being my test quotient for equilibrium if I'm starting off with initial concentration values. And then R standing for my ideal gas constant, T standing for temperature. Okay, in the previous video we said that delta G was also equivalent to a negative N times F times E. So number of moles of electrons times Faraday's constant times cell potential. So I just plugged in this for delta G. So I would get a negative NFE equals a negative NFE, but this is going to be at standard conditions, and then plus RT, L, and Q. Okay, so just stay with me because this is what Nernst is thinking about when he's trying to derive this equation. Okay, so let's divide both sides by a negative NF. And we're doing that because ultimately I just want to get E by itself. I want to see what's the cell potential going to be at non-standard conditions. This is my goal, or at least in Nernst's mind, that was his goal. How can I generate cell potential under non-standard conditions? And more specifically, how can I even calculate it? So non-standard conditions would be where I'm just trying to find E, because in standard conditions would be where we have the E naught. Okay, so if I divide everything by a negative NF, I'm going to get E is equal to my standard E minus RT over NF, L, and Q. Now, ultimately, we can try to simplify some things down, use log base 10, or base 10 logarithms, and I can get, E is equal to E sub naught, or E naught, minus all of this log Q. Let's simplify that down, though, even more, because ultimately, I know that temperature at room temperature is 298 K. I also know what R is. So if I just simplify down even further, do you have to know how to simplify this down? No. But ultimately, I'm just showing you all the work of how to do it. So the equation, Nernst equation, is going to be this right here. E equals my standard cell potential minus 0.0592 over N just meaning how many number of moles of electrons we are transporting or transferring, times a log of Q. And Q, remember, is still equilibrium, but specifically this is going to be using concentrations to determine something that is happening at an initial state. So we can find what this means. We can calculate cell potential or electromotive force, because remember we can use those words interchangeably, under non-standard conditions. So I'm going to still use the standard condition, but the rest of this is going to apply for a non-standard condition. And that's how I can calculate a non-standard condition of cell potential, which is E. Okay, so in this question, we're just going to be utilizing the Nernst equation. So for this one, I would also just like to wait until we have tomorrow at the beginning of class. So will someone remind me that we need to do slides 53 and 57. So slides 53 and 57 we'll do at the beginning of class, and then we're going to review. We're going to review for all the stuff over chapter 20. How do I use this stuff? What would it look like? And also I posted a practice test on your blog last night. So if you also want to try to work on that after you've watched these videos, then hopefully everything should make sense, should be easy to do. And if not, then bring those questions to class tomorrow because we can work on them also in class. So we'll do this problem together in class. Okay, concentration cells. So a concentration cell is just a cell that's based solely on electromotive force that's generated because of a difference in concentration. So ultimately in a concentration cell, we're just going to be utilizing a different amount of concentration to generate some amount of electron flow. And a voltaic cell is similar, except usually we think about the concentrations as being standard, so usually they're 1 molar concentrations. But in a concentration cell, I can still generate electron flow or current because I can change concentration to get the same kind of effect as what we were doing with the voltaic cells.
Excuse me, everyone. I need to read
And then this is an example of this, but I'm not going to focus on this one because concentration cells really aren't so much focused on the AP test. So really the rest of this chapter is just applications of redox. So we can talk about batteries, hydrogen fuel cells, as well as corrosion. I am not going to focus on those things, but your book does a pretty good job of talking about them. So if you would read in your book, please, just about these applications, that would be amazing. And I again will go through slides 53 and 57. And if you have any questions, post on your blog. I know this was really quick, but we'll really hit, I think, more on doing practice with delta G, K, as well as delta E, or just E, in general, tomorrow in class. So have a really great night, guys. Stay warm, and I will see you tomorrow. Bye!